Hi, this video is lesson 4, module 7. We're going to be looking at molecular shapes. So we've done the Lewis structure drawings, and then now we're going to look at the actual three-dimensional shapes that molecules take, which is really important for kind of why molecules act and behave the way they do. We are using a theory called the valence shell electron pair repulsion model, and it the acronym kind of stands for what it is. So valence shell electrons around the central atom are always in pairs. They're either in a bond or bonds, or they're lone pairs, and they're negative, so they're going to repel one another. So the bond angle, once they repel each other, they're going to have kind of a fixed angle between them that helps them get away and repel as much as they can from one another. So the bond angle, I'm just kind of showing you, like, if I try to push these closer together, I can kind of temporarily, but they're going to kind of spread out and end up as far away as they can be, which for this particular shape is 120. And I can show you a little bit more. So like here, this is the sticks themselves are representing a single covalent bond, so electrons, and they repel each other. So they're going to, get away from each other and spread out into a 180-degree angle. If I add a lone pair, there's electrons on the central purple atom. They're not bonded. They will kind of push those and repel those other negative electrons away. The more lone pairs, the smaller that angle gets. It's weird. It didn't show it, but it should have been. It kind of should have got a little bit smaller. So, yeah. So back to the notes. So just a real life application of the shapes of molecules and how important they are. There are really a lot of connections to biology and organic chemistry, pharmacology. SSRIs are serotonin reuptake inhibitors that we use for anxiety and depression. There's, I don't know the exact mechanism, but there's a way that it can kind of interfere with the natural ability to uptake the serotonin back into the body, which then results in there being more in the system, which can help people to feel better. Taste buds are another example. The taste buds themselves are kind of have an opening, and only certain shaped molecules will fit and then stimulate the nerve, which will then transmit to like a sweet taste or a sour taste. Hybridization. This is just, so in real life, we have hybrid cars that are kind of in between gasoline and electric. We have a lot of hybrid types of vegetables and, those fruits like an apple pear where they kind of combine and you get traits of both. Similarly, in chemistry, what'll happen is the atomic orbitals will kind of fuse together and form a whole new set of orbitals that are similar but different than each of the originals. So in this diagram, you can kind of see this is CH4, methane, and you can kind of see the remnants of the P, dumbbells, and then also the S kind of morph into these weird shapes, which you don't need to know the shapes, but I'll kind of explain it. The drawing over here does, but I think it's easier to explain it if I draw it. So carbon is 1s2, 2s2, 2p2. So if we were going to draw the orbital diagram, we would have the 1s, the 2s, and the 2p with a little bit more energy. And if we do that, this is what carbon looks like. But when it's going to bond, this hybridization only occurs when it's going to bond. These orbitals will kind of merge together. So one of these s electrons kind of jumps into the p, and they end up all at the same amount of energy. So we call that sp3 hybridization, because now you can see S, like there's an original S in these three P's. So now I'm going to start to fill out the note sheet that I hope you have a copy of or write this into your notes. So the first thing, A is the central atom, and I'm not going to try to draw these with the real shapes. I might for a couple, but it's not really worth it to me. So A is the central atom, X is just any other atom that's bonded to it. So we're always interested mostly in the central atom. So for example, C, Cl, Cl, H, H. So mostly this is a tetrahedron. Most tetrahedrons have carbon in the middle or silicon. This angle looks like 90, but in reality it's about 109.5. So we have 4 bonding areas. So I say bonding area, not just bonds, because sometimes you'll see in the coming up that there can be more than one bond. But so there's 4 bonding areas. There's no lone pair. I'll show you what a lone pair looks like soon. And then we use this ABE notation. So we say A is for the central atom, B is for the bonds, and there's 4 of them. And then I don't write the E. We're going to leave that last column until later. So trig, oh, and by the way, this is sp3 hybridization. Notice it adds up to 4. So trig pyramidal is going to have a central atom with 3 others coming and being off of it bonded with 1 lone pair. So an example of this is ammonia. So you can see that there's 3 bonding areas and there's 1 lone pair. So the lone pair of electrons are these kind of the dots on the top that aren't bonded. And remember, that kind of pushes it down. So the angle now is smaller at about 107. So we would say that this is AB3E1. Okay, next one is bent. So now we're going to have a central atom, and we'll have 2 elements bonded with 2 lone pairs. So example of this is water. You can try to bend it when you draw it. I don't. But in reality, we know that, and if you use the PHET, that those lone pairs kind of push down the bonded electrons and make that angle get even smaller at about 105. So here we have 2 bonds and 2 lone pairs. So it would be AB2E2. Again, the total is 4. So it's sp3 hybridization for both of these. Lastly, we have linear. Linear is going to be just 2 elements this time. And you can just pick one that you're going to consider to be the central atom. And now, in order to get the maximum distance from each other, they're going to be in a 180-degree angle. Example would be HF. And that would be my central atom. And you can see that we have, 1 bonding area, and then 3 non-bonding areas. So 1 and 3, it's going to be A, B,